So our last little topic here for this unit is to talk about some basic probability. Probability is also about predicting. Now what we kind of just did with the bell curve is a form of probability. Saying that we would expect 15.87% of all values to be above a certain value. That is giving a probability. We're expecting 15.87% to have this characteristic, even though we haven't looked at them yet. That's a probability. Probability is predicting future events. But it's not predicting the result of the event itself. It's actually predicting several results. And what it is the likelihood. Wow, I better sit down so you can read my handwriting. It's predicting the likelihood of each possible result. The most basic law of probability is that we have a desired result, what we call a desired outcome. An outcome is just a result. And then we have all of the possible outcomes. And if we can count all of the possible outcomes, we can calculate a probability. For example, let me give you a really simple one here. If I roll a die, what is the probability of rolling a 4? Well, all of the possible outcomes here, there's 1, 2, 3, 4, 5, or 6. Those are the only possible outcomes. There are 6 of them. With all the possible outcomes. But now we have the desired outcome. How many of the desired outcomes are in this list? 1. There's just 1 4 in that list. So the probability is the 1 desired outcome divided by the 6 total. We can just leave it as 1 out of 6, or we can divide it out to be 0.1667, however we want to leave it. If I put the numbers 1 through 10 in a box, put them on ping pong balls or slips of paper or something, throw them in a box, and I reach in and I pull one out, find the probability of drawing out a 2. What's that going to be? There's only 1 2 in that box out of 10 possibilities. 1/10. Or 0.1 if we want to put it as a decimal. Either one would be acceptable. What is the probability of drawing out a 3 or a 7? Well, there's 1 3 and there's 1 7, so there's 2 desired outcomes. Either one of those would be desired out of 10 total. So that can reduce to 1/5 or 0.2 if you want to put it that way. What would be the probability of drawing out an odd number? Odd, of course, 1, 3, 5, 7. How many odd numbers are in that box? 5 out of 10 total. So that's 5 out of 10 or 1/2 or 0.5. It was a decimal. Not so bad? Okay. We can have combined probabilities of more than one thing happening at once. For example, you might roll a die and flip a coin at the same time. Let's say you want to know what is the probability of rolling a 5 on the die and getting heads on the coin. Well, we're going to look at each. So these are what we call independent events. Whatever you get rolling the die, does not affect what you get flipping the coin. They're totally independent. So what that means is we can look at each of them separately. What is the probability of rolling a 5 on the die? 1 out of 6. There's 1 5 out of 6 possibilities. What is the probability of getting heads on the coin? 1/2. Since they're independent, we're just going to multiply them together. 1/6 times 1/2 is 1/12. Try to make it as a decimal, 0.0833. That is independent events. The result of one does not affect the other at all. Let's take another example, and we'll get around to, well, if there's independent events, obviously somewhere there has to be dependent events. So let's get to where we can get to an example of that. Let's do, now we're going to put marbles in a box. And let's put in 30 red, 20 blue, and 50 green. Now I'm just going to use some notation here. It's kind of shorthand to speed things along. P with the parentheses is asking what's the probability of getting whatever is in the parentheses. So what's the probability of reaching into that box and drawing out a red marble? Well, there's 30 red marbles out of 100. So 30 out of 100, or 3/10, or 0.3, however you want to write it. I would actually accept the 30 out of 100 too if you didn't want to reduce it. What's the probability of reaching in there and pulling out a blue marble? 20 out of 100, or 2/10, or 1/5, or 0.2. This next one's a little bit tricky. What is the probability of reaching into the box and pulling out a red marble followed by a blue marble? Well, in this case, you might be tempted to jump in and start doing some number crunching, but right now we do not have enough information. What we need to know is if we reach in, well, first of all, if we reach in and we draw anything but a red marble, we're done. It doesn't matter. So to calculate this, we need to find that probability, but then we need to assume that we get the red marble. So we reach in there, we get the red marble, so we're okay. But we need to know before we reach in to grab the second marble, what do we do with the red one? Do we put it back? If we put it back, the statistical term for it is called replacement. The marble is replaced or put back into the population. Or do we toss it aside? That is called no replacement. It is not replaced or put back into the population. How is that different? Well, if we draw out the first marble and we put it back before we draw the second marble, it's independent. Just like we were talking about with the die and the coin. What is the probability of reaching into that box and drawing out a red marble? Well, 3 out of 10, right? 30 out of 100 or 3 out of 10. I'll put the 30 out of 100. If we put that marble back before we draw another one, what's the probability of the second marble being blue? 20 out of 100. Perfect. Because there's 20 blue marbles and there's 100 in the box. So this ends up being 6 out of 100, or 0.06 is the probability of doing this. If we don't replace it, if we toss it aside, this is an example of dependent events. Because the probability of the second marble depends on what happened with the first. We reach in there, what is the probability of that first marble being red? It's still 30 out of 100. Good. But now, what's the probability of the second marble being blue? How many blue marbles are there? Yeah, there's still 20 blue marbles, but now there's only 99 total marbles. So that is 30 out of 495, or what? 0.0606. Because we've already done something to the population, the probability's changed. The probability of drawing a blue marble depended on whether you'd already drawn a marble or not. So they're dependent events.
Something like that would you technically there is on the same.
You would want to put 0606. So what's the probability of reaching in and drawing out 3 green marbles if I draw them out one at a time and I replace them? Well, what's the probability of the first marble being green? 50 out of 100, or 1/2. What's the probability of the second marble being green? Why is it still 1/2? Yeah, put the first one back. How about the third marble? 1/2. Good. We multiply that up. That's 1/8 or 0.125. Either one. Again, I'd probably stick with the fraction of the 1 out of 8. What if we switch that up to where it's no replacement? All this is going to get to be a lot uglier fraction. What's the probability of the first one being green? That is still 1/2. Second one being green. Careful. They're the same color now, so there's only 49 green ones out of 99 total in the box. How about the third one being green? 48 out of 98. Very good. So now we've got the 49 times 48 times 1 on top, the 2352. On bottom, we have 2 times 99 times 98. So 19,404. Looks like some really ugly numbers. Let's just divide them out. .1211. So it is less likely to draw 3 green marbles if you don't replace them, because you're taking green marbles out of the box. There's not as many in there after the first draw. Does that make any sense? Nope, 2,352. Oh, I did. Sorry. 2,352. Good call. Divided by 19,404. So 0.1212. Thank you. There we go. What's that? Okay. Okay. Any questions? Is that making sense? I feel like I really cut it short in the second hour here. But that's really all we have for the test. Usually there's a lot more questions on the homework coming out of our probability week, so I usually give a lot more time. So that is it. There is a new quiz due tomorrow. So that is Wednesday at 11:59 p.m. There's a new homework, and yes, I realize that there is a technical error in this homework as well that I will get changed due next Tuesday. I got to change the date to 2015 instead of 2014, otherwise you're not all a year late.